So, good morning, everyone. I hope that you all enjoyed the weekend. I thought it was pretty good. And hopefully I'll be able to give you some feedback on Wednesday and Thursday on the exercise. We're marking it today. And as I mentioned in the tracks, this week track probably will be somewhat shorter, maybe an hour and a half, and then we'll have a 3-hour slot. I thought about Thursday, the 12th of November in the afternoon. So that sounds like it's 5 days before the exam. You have the whole weekend to keep thinking about and keep basically learning for the exam. Does that sound right? 5 days? So I will check availability and we'll send a message on Blackboard, probably let you know on the prac this week as well. But yeah, as I mentioned, this week prac, I don't prepare anything. We don't solve any particular exercise. Just I can give you whatever information you want on the exam, and you should ask me questions on anything that is unclear, either related to the prac, the project, or most importantly, to the lecture material. Now, I will continue with the lecture that I started on Thursday, and that's the last lecture, so it will take us all the way to Thursday this week, and it is really, really important because it puts everything together. It's exactly the kind of questions that you'll find in the exam. So it's really important that you understand all the concepts here. And on Thursday, we will hopefully be able to kind of summarize and try basically to see that we understand all the concepts that were learned during the semester. But this is where we stopped last week, and it is a pretty dense slide. It has a lot of information that essentially we get from an outcrop. So we have a little outcrop here. You see the sketch of the outcrop. And we don't really see folds in the outcrop, but we think that this area was affected by folds because the rocks are strongly cleaved. So we see the subvertical or steeply dipping axial plane. Well, we see foliation, steeply dipping foliation. It's a secondary foliation. We see the primary foliation is horizontal. We can see that by the banding of the different compositions, yes, or the colors. So bedding is horizontal, and there's a strong cleavage, and we think if this is an axial plane cleavage, then it may represent the axial plane orientation of folds. If so, where are we relative to these folds? That's basically what we're doing. We'll not be able to understand the scale of those folds using only one outcrop. We'll need to go to the next outcrop and the next one and start basically working out the scale. But we know that we are somewhere relative to larger scale folds. It could be 100 meters or 1 kilometer or 10 kilometers. That's something that we need to work out. But there are other things that we need to understand is whether this fold is an antiform or synform. So where are we relative to the antiform synform? Where are we relative to the anticline syncline? So we need to understand the stratigraphy. What is young and what is old? And what type of fold is that in terms of the orientation? So what do we call this fold? Is it an upright fold, upright plunging fold, vertical fold, recumbent fold? So using the classification diagram that you had in the field, what is the orientation, the attitude of the fold in space? We can get all that information from here, and that's exactly what we'll do in the next 2 lectures. The other thing that we get is information on strain. Okay, so in the last question in Shorncliffe on the weekend, I asked you what is the orientation of the maximum shortening. And it's an easy question if you think about the relationships between folds and strain. The folds are going to be produced perpendicular to the maximum shortening. So if I apply horizontal shortening in that direction, it is the axial plane that is exactly perpendicular to the maximum shortening. So I know something about the z-axis of the strain ellipsoid. That is the axis that is perpendicular to the axial plane. The actual plane will be the XY plane of the strain ellipsoid. The stretching lineation will give me information on the maximum stretch, on the X direction. So if I have a combination of foliation and lineation, and stretching lineation, then I can take, I know how to construct the strain ellipsoid. I don't know the magnitude of the strain ellipsoid, so I don't know the ratio. It could be a very large ratio between X and Z, or it could be just a small ratio. For that, I need to do quantitative strain analysis like you did in the lab project. But I can immediately, just from the orientation, know the general orientations of X, Y, and Z. Okay, so geometric and kinematic information. And all that is produced from one outcrop here in the field. So that's exactly what we'll do. But before we start doing that, we need to make sure that we understand properly the terms, what exactly we mean by Younging, how do we find information on the relative stratigraphy, what is young and what is old. Vergence is a term that I mentioned a few times during the semester, but we need to make sure that we understand exactly what it is, and we need to make sure that we know how to use it now in terms of when we are out in the outcrop. So I will talk a fair bit about vergence, and I will just reiterate material that we already know on macroscopic folds. So what do we know about fold orientations and relationships in the map view and these kind of things that we saw, for example, in the Broken River map in the last track. So let's talk about these three things and then get back to this slide. So stratigraphic Younging. I hope that all of you made the observations in Shorncliffe, for example, of these structures. Yeah, they are sedimentary structures that basically tell us something about the process of sedimentations. We have piles of sands that are deposited on top of each other and then creating these kind of laminations or these kind of fine layers. And then we have another pile that truncating the previous one and do exactly the same thing. So the truncation surface is always the top of each pile. Okay, so we know that here is a truncation, here is another truncation. It is always the top of the pile, and below we have these kind of asymptotic relationships because the grains are just kind of lying parallel to the existing surface. Okay, so these are soft sediment kind of processes. What we see is a solid rock, but we need to think about the processes that are associated with sedimentation. The important thing, these are all things that are not really related to structure geology, but they are crucial to us because when we make these observations, we know, is the rock right way up or overturned stratigraphically? Is it upside down or is it in the right order? And something like that is in the right order. There are many others. I put here only 4. There are lots and lots of them. Those of you who will take or already took sedimentology will learn a lot about that. But wave ripples, for example, we get kind of a cusp shape that go upward just from the way that the wave action is affecting soft sediments. We have mud cracks, so similarly to what we see in areas that undergoing cracking, fracturing and cracking in mud. Then the holes basically are filled with sand, so that's what we see here. And in a cross section, we'll get a kind of V shape. So the sand basically, there's a kind of a hole like that. So these things basically tell us that this V will always point downwards. Okay, here we see the upward section. Then we have graded bedding. We talked about that a few times. So just from, again, it's basically generations of sediments that have different grain sizes, and the coarser material will be deposited first. Then we have finer and finer. There's kind of sorting because of the energy of transportation. The finer material are those that can reside in the fluids, whatever it is, in river systems or in the continental shelf. and reside longer and therefore being deposited at the top part. So we get coarser material and finer and finer material as we go upward. The important thing is that all these structures basically tell us what is old and what is young, relative, essentially the relative age of the rock. Okay, so that is younging, and we'll get back to that later when we look at rocks. Then we need to talk about vergence, and I think I had exactly this slide already before, maybe even twice during the semester. The vergence essentially an indication for asymmetry in rocks. So we find vergence, essentially, strictly speaking, it's essentially the sense of overturning. We have an overturned limb here, and this limb is rotating clockwise. Or we can say that the vergence is to the right. I always look at what happens to the top here. The top is moving to the right. Okay, so it is the sense of asymmetry, and another way of looking at that is to think about the relationship between the fold axial plane and the enveloping surface. So the enveloping surface is the plane, it's an imaginary plane that connects all the hinges of the same layer. You remember we talk about axial plane a lot. The axial plane is the plane that connects all the hinges of the same fold, but different layer. The enveloping surface connecting all the hinges of the same layer. And we define vergence if the angle between the axial plane and the enveloping surface is less than 90 degrees. Yeah, if they are orthogonal to each other, then there is no vergence. These are symmetric folds, as we see here. And if there is certain, or if there are oblique relationships, then there is a vergence. And you see that the folds are kind of tilted here towards the east. So there is a vergence to the east here. Yeah, it's essentially exactly the same as we saw before, just different ways of looking at that. And we'll see today how in the field, when we are standing in front of an outcrop, and what we see is only the bedding and the cleavage. So the cleavage is the axial plane orientation. How do we define the vergence? And there's a kind of rule of thumb of how to do that consistently, and always knowing how, making the observation saying the vergence is to the east or the vergence to the west in a consistent way, and I'll show that to you soon. Okay, so vergence, that makes sense? Okay, I think we also had this slide before. We can look at the vergence in relationship to a thrust system, for example. So there is a sense of movement on the thrust, and all the folds have an asymmetry that represent this movement. Or we can look, and that's the major thing that we'll do today, we can look at the vergence, at asymmetries that are related to our position in a larger scale structure. And that's the important thing, because as I mentioned many times, in structural geology, what we see in small scale represents the larger scale. So we basically have kind of repetitions, a kind of a fractal behavior of features, and we recognize smaller symmetry, and it represents something larger. And that's what we see here. If there's a fold here, there will be smaller scale folds here, parasitic folds or minor folds, whatever we call them, that will show asymmetry because they are oriented on at the limb of a larger scale fold. So ZSM folds. Yeah, we talked about that. Of course, if we have the processes of flexural slip, the process itself will be responsible for creating asymmetry. But even without that, just the disharmonic folding, the fact that we have smaller folds, their orientation will be asymmetric relative to the larger scale structure. Okay, so what really the vergence tells us in these situations is the sense of closure. So you see that basically the vergence that we have here on the Z fold is essentially vergence towards the antiform. And here it is vergence towards the antiform. It is always basically leading us to the next antiform. That's the beauty of that. We go to an outcrop, we find the vergence, and we say the next antiform is going to be there. Okay, so we can do that in a neutral in non-neutral folds, or antiform, synforms, we can find the next antiform. And if you remember, there are a few folds that we cannot call them antiforms or synforms. These are neutral folds, like recumbent or vertical folds. So essentially, we talk about clockwise, counterclockwise versions, and we are basically led to the next closure. Okay, let's talk a little bit about fold geometry in a larger scale, because we'll relate to all that. You're supposed to know all that already from the lectures, but we'll relate to that, and if you don't remember, it will make it more difficult to understand what we're actually doing in the outcrop. So first of all, the fold has a certain geometry, which is defined by the dip of the axial plane and the plunge of the fold hinge. Yeah, we all know that. That's exactly what we try to do in the field on the weekend. And we see that if we know the fold hinge, anything between horizontal to vertical, the axial plane, vertical to horizontal, we can come up with different attitudes of folds. Some of them are non-neutral, so antiforms or synforms, and some of them are neutral, like reclined, recumbent, and vertical. They cannot be defined as antiform or synform. And we have all the different names. All the ones kind of in the middle are basically just, they have the names of plunging, incline. So moderately plunging, steeply incline, moderately plunging, moderately incline. So just combinations of what the axial plane, the fold plunge and the axial planes do. And then we have a few kind of special names for end members: reclined, recumbent, upright, and vertical. So that's the fold geometry. And then we need to distinguish, of course, between the actual structure and the stratigraphy, so synforms versus antiforms, and how they appear, synforms, antiforms, synclines, and anticlines, and the way they appear in a map view. So again, something that we talked a lot recently in the Broken River map, and this is the Broken River map that we worked on last week. We see that we can make the observations on the map and work out whether it is an antiform, synform, anticline, syncline. So here is part of the map, the one that we made a little cross-section. This is the axial plane. What we see on the map is the axial plane. It is the strike of the axial plane. We don't know the dip and dip direction. That's what we did in the weekend, once we have some more information. So that's the axial plane. And here is what the structure does. So the structure, the bedding is going into the structure. So that is going to be a synform, right? It is a structure that is that the bedding orientation is going into the structure. So it's a synform, and the fold plunge, therefore, is going into the structure as well. So always in synforms, the plunge is going into the structure. It will not necessarily go into the structure exactly in the orientation of the axial plane. It can go oblique, it can be oblique to the axial plane if the fold is inclined, and I'll show that in the next slide. But the important thing is that synforms will have plunge that is going into the structure. Antiform will have plunge that's going away from the structure, so that's what we see here. And neutral folds will have a plunge that will go perpendicular to the fold to the strike of the axial plane. So it doesn't really, you can't really define whether it goes in or out. Okay, so how do we do? Well, just one thing before I go on, actually. The other thing that we see here is the stratigraphy. So those of you who did the exercise know that the gray units here are younger than the purple ones. They are the Carboniferous, and those are the Devonian. So we have younger rocks in the middle of the structure, and therefore that is going to be a syncline. So it's a synform, and it's a syncline, which is most of the time is going to be the case unless the rocks are overturned. Yeah, so if you want to have a synform and an anticline, then we need to have a pretty complex history, because we first need to overturn the whole thing, and then we need to create the sin form. So you basically need 2 generations of faults, and the first one needs to be pretty extreme in a way that it will overturn the whole thing. It's possible, but it's of course less common. Okay, and just one more slide in relation to the relationship between the fold hinge and the orientation of the axial plane. We can see that this could vary, so it basically depends on what the dip of the axial plane does. So what you see in the map view is the strike of the axial plane. And you see that here, in all these examples, the strike is exactly the same. Yeah, the strike is basically this red line. It is the line that you can connect on the map. You can find the strike of the axial plane just by taking all the closures, connecting all the fold hinges, and you find this red line. But you see that here the axial plane is vertical, here it is inclined, and here it is inclined as well, and depends on the level of inclination. You can get different orientations. So here you get something that is a kind of oblique relationships, and this is basically what happens in reclined folds. So the strike of the axial plane is actually perpendicular to the fold hinge. Okay, so we need to keep that in mind, and not make the assumption that all folds are going to be, all fold hinges are going to be always parallel to the strike of the axial plane, because that's the kind of intuition we have when we look at maps. Okay, and the last thing about folds is that we need to remember that the only way for us to understand what folds are doing is to look down the plunge. Okay, so again, I mentioned that already. This person is not really able to appreciate the fold geometry, and the photographer is basically seeing here the bedding changing, the axial plane is going like that. So basically the intersection of the axial plane and the bedding is what the fold plunge does, and it is exactly perpendicular to the photographer. Right? So this is the intersection, and that is what the fold plunge does. Now, in general, when we do this kind of field geometrical analysis, what we always try to do is to look down plunge and not up plunge. And the reason for that, we'll start basically defining vergence and saying the asymmetry is towards the west or to the east. And surely if you do it from the opposite direction, you'll get a mirror image. So consistently, we always say, when we look down plunge, that is the sense of symmetry that we recognize. And if I come to an outcrop that it is basically impossible for me to look down plunge, then I write in the notebook that now I look up plunge, I get vergence of such and such, like vergence to the west, but it's actually equivalent to vergence to the east, because what I see is a mirror image. So just in terms of consistency, you'll see later on why these things are important. Any questions so far?
So to look down plunge, where are you standing, like where S1 is on the picture?
I will stand exactly where the photographer is. So basically, I will look for the intersection of the bedding and so this is the cleavage, the axial plane cleavage. This is the bedding, and the intersection is a line. So I can take my pen and say, okay, the intersection goes like that. Sometimes I will find intersection lineation as well. And I say, is the intersection plunging away from me or towards me? If it plunges towards me, then I look up plunge. If it goes away from me, then I'm looking down plunge. Yeah, sometimes I will find actual little folds. Yeah, so I see basically that the fold hinges are going, plunging away from me. And the important thing is that I never look oblique or orthogonal, because then I don't even understand, the projections just look kind of funny. I don't even recognize the folds. I think that many of you who came to the fold, for example, in the northern area in Shorncliffe, didn't quite see the fold until you were exactly in the right position, looking down plunge. Yes, so if you were a little bit oblique, you thought, what is going on here? I don't see any structure here, just because it is hard to actually observe it unless you look in the right orientation. Okay, so we're back here, and we can start obtaining the geometrical information on an outcrop. Okay, so what we look first is we look at the vergence, and then we'll deal with younging. So here is an outcrop, and I don't see any folds in the outcrop. What I see is bedding and cleavage. Okay, so what I get from this outcrop, I can measure. I can put the compass and measure the bedding. The bedding is dipping, say, 50 degrees to the left. Right? I can take this measurement. I can put the compass and measure the cleavage, and I get vertical cleavage. That's already kind of immediately when I see the vertical cleavage, I say, if this is related to a fold, the axial plane of this fold is likely vertical. So it's going to be an upright fold. Okay, so you can be really quick in that. Yeah, you come to an outcrop, you look at that and say, there are probably upright folds in the area. Okay, but upright fold is only half of the name of a fold. Yeah, that basically means that the axial plane is vertical. But as we know, the folds also have a fold hinge, and we can have a plunging upright or horizontal upright folds. And that's exactly what we get from the intersection unionation here. So if we have cleavage and bedding, we can immediately either measure, either find the intersection unionation or calculate the intersection unionation. Yeah, we can take basically a stereonet or just a geocalculator that will tell us what is the intersection of this plane and that plane, and that will give us the intersection unionation that is going to appear here is, of course, as a dot. Say it is horizontal here, then we know everything about the geometry of this fold. Yeah, we know that this fold is an upright horizontal fold. Yeah, just from 10 seconds, of approaching the outcrop. So bedding, we can take a measurement. Cleavage, intersection unionation is the intersection. We can either look around and try to find a place to measure directly, or we just calculate it. We can put it in the stereonet, see the intersection. Okay, now what does this tell us about the larger scale structure? So in order to do that, we will look here at a fold. So let's first see a fold that we already have the structure. We understand the structural relationship, we understand the stratigraphic relationships, and see the different parts of the fold. Then we'll go back to those outcrops and kind of relating them back to this situation. So what we see here is an antiform. Yeah, it's an antiform with the structure basically dipping away from the structure, and it has an axial plane cleavage. The axial plane cleavage is the same everywhere, and that is really that's the crux of the exercise, because if the axial plane is not the same everywhere, these relationships are not going to work. So basically, you can do this kind of geometrical analysis only if you have an orientation here that is repetitive and basically changes the angular relationship between the two limbs and the hinge. Okay, so we know that it's an antiform. We know that it is we know the axial plane. We also have stratigraphic information, and that comes from the sedimentary features. Okay, so this is what we see here. We see here that these are coarser grains and these are finer grains. So this is graded bedding. We see also look at the cleavage refraction. Yeah, when we have the coarser material, the coarser grains, we get refraction to higher angle of the cleavage, and it is in the finer material that the cleavage is more or less parallel to its real orientation of the axial plane orientation. So what we see here is that the coarser grains are above the finer grain. That's exactly the opposite of what we saw before as the way it should be. Yeah, graded bedding, always the coarser grains are below and becomes finer and finer as above. that is exactly the opposite. So this limb is overturned, yeah, stratigraphically overturned. And this limb is stratigraphically right way up. Now, if this is overturned, that means that these rocks become younger here, older here. These rocks are younger here, older here. So the center of the structure is where the older rocks reside. That makes it an anticline, right? So it is young, old, young. It's an antiform and it's an anticline. And we already said that this limb is stratigraphically overturned, but let's now look at the structure. It is also structurally overturned. And we see these relationships because we see that the bedding becomes steeper than the cleavage. So both limbs are dipping in the same orientation. This limb is an overturned limb, and in the overturned limb, the bedding becomes steeper than the cleavage. In the right way up limb, the cleavage is steeper than the bedding. Okay, so we find these kind of relationships. We look at bedding, cleavage orientations, the relative dip. We look at the younging, and we get information both about the structure and the stratigraphy. Okay, so the structural facing is what we call is the actual structure, regardless of the stratigraphy. And structurally, this limb is right way up, this limb is overturned. And that is because the bedding here is steeper than the cleavage. Stratigraphically, this limb is right way up, this limb is overturned, and that is because the younging is going downward in the overturned limb. Does this make sense at all? Now, that's as I mentioned before, that will be the case in most situations, but not in all. And we can look at an example, I think, in the next slide, where we get more complicated relationships. But let's see how we actually do that. So when we actually come to this out of here, how can we work out the structural facing, the divergence relationships? And the way that we do that is basically by looking at the relationship between S1, so the axial plane of the first generation folds. We do this exercise with one generation of folds. If we have more than one generation, it becomes more complex. So we deal here with one generation of folds, the same axial plane. We have S1, and that is dipping here, say 60 degrees to the west. And we have the bedding that changes its orientation because of the fold. And the bedding is S0. What we're going to do is basically look at the sense of rotation from the cleavage to the bedding. So basically kind of take our hand, put it parallel to the cleavage, and rotate it back to the bedding. And then we get some sort of rotations. I'll show you exactly what I mean. So here is the bedding, here is the cleavage. We always start with the cleavage. We always start with the youngest feature. So the cleavage is the young is the latest feature compared to the bedding. We start with the cleavage, I rotate it to bedding, and this rotation will be clockwise rotation. Yeah, basically with the upper part going to the east. So basically what it gives me, so this is cleavage, that's bedding, I rotate it, and I get divergence to the east. Okay, if I do that in the other part, in the other limb, I get the cleavage like that, the bedding, and I rotate the cleavage to the bedding, and I have now counterclockwise rotation, and if I look at the upper part, it's divergence to the west. Okay, so basically that's what I do, and that's exactly what we do in the field. Yeah, I go to the outlook, say, okay, cleavage like that, bedding like that, take my hand, say divergence to the west. Okay, it's really quite straightforward. The important thing is that you do it systematically, and as I pointed out before, I need to look down the plunge, because if I make half of the observations up plunge and half of them down plunge, then I start to see mirror images of the same features. Okay, so you see divergence here. It's basically indicated by an arrow, and the arrow is pointing to the next antiform. So I basically visited two localities here. I don't even see the hinge. You see that the hinge is not really clear here because I don't have any stratigraphic marker exposed. Yeah, the hinge is basically all eroded here. But I walked here, I knew that the next antiform is going to be to the east. I kept walking to the east, I found another outcrop. I did the divergence exercise, and the next antiform is to the west. My conclusion is you just pass the hinge. Yeah, the hinge was exactly here, at the surface. Yeah, I didn't have the marker to see it, but it was there. Now, the relationships at the hinge is where there's no vergence. So if you come to the hinge and you do recognize bedding and cleavage, as I mentioned before, here we found only cleavage, but let's say that we did have a stratigraphic marker, we did find a bedding. At the hinge, I will have bedding, I will have cleavage, I will have bedding, and you see that they are orthogonal to each other. So basically, there's no vergence. So always, if you do end up in an outcrop with bedding and cleavage perpendicular to each other, you think, I'm possibly actually standing at the hinge of a fault. Okay, here is a slightly more complex situation. So we have bedding here and cleavage here. So let's talk about the structure first. Well, first of all, is it a synform or an antiform? Yeah, synform, we immediately see that. And bedding here is steeper than cleavage. So is that structurally right way up or overturn? Overturn, yeah. Bedding steeper than cleavage, bedding shallower than cleavage. So this is right way up, this is overturn. Now we look at the stratigraphy at the Younging, and we see coarse grains here, finer grain below. Is that Younging to top or bottom? Bottom. So it's going to be stratigraphically overturned. Okay, so structurally right way up, stratigraphically overturned. And here we see that the Younging it's quite steep, but the Younging is still above. So it's stratigraphically right way up and structurally overturned. So things here are really messy. And as I mentioned before, we need to come up with a more complex explanation for that. Okay, so that's what we did now. That's all good. In terms of Younging, we know that the old material is actually in the center of the synform. Yeah, we know that from the Younging. It's Younging to the bottom here. And so we call that an anticline. Yeah, it doesn't look so intuitive, but this is an anticline. It's a synform, and it is an anticline. And the only way to explain that would be something like that. Yeah, so we had a recumbent fold, yeah, fold with the horizontal axial plane, and we are at the overturned limb of this recumbent fold, and then the whole thing got folded again. Okay, so we do find these kind of things. For example, if we go to the Swiss Alps and we see these huge nap systems, so huge recumbent folds. Yeah, each recumbent fold could be kilometric in scale. So basically, we get whole successions that are completely upside down on the overturned limb of those recumbent folds. And then all you need is a little bit of shortening, of additional shortening in a different orientation in order to create antiform and synforms that will actually be synclines and anticlines. Okay, let's look at this example. I looked at this slide this morning, and there was a mistake in it. So if you printed it, please make sure that you correct. And the mistake was with the Younging direction. We'll talk about that soon. Let's first look at the cleavage and bedding relationships. So we see the bedding here. Okay, and we need to make sure sometimes bedding becomes the most complex kind of feature to see. Yeah, we need to make sure that what we see actually is the bedding. I see the bedding based on the color changes and maybe indicating different grains, so coarse and finer grains. We will talk about that soon. So, but I'm convinced myself that this is bedding. dipping to the right, and the cleavage is also dipping to the right. Yeah, the cleavage does that, and the cleavage is not. You see that the cleavage is kind of wavy, and that is really the indication, the best indication for younging. What we see here is evidence for is basically the effect of refraction. Okay, so the cleavage basically is at a higher angle in this part of the layer, and then becomes shallower at lower angle in this part. It basically tells us what is weak and what is strong. Okay, weak part of the layer, strong part of the layer. We get more refraction in the more competent part of the layer, in the coarser part. And this is why the younging is right way up. Okay, for some reason I had here on the slide the opposite information. I wrote that the younging is opposite, but it is right way up. Yeah, from strong to weak, from coarser grain to finer grain. So what we see here is graded bedding, and we recognize that by looking at the way that the axial plane is refracting. It is the weaker, finer grain material that will have less refraction, will be closer to the actual orientation of the axial plane. Okay, but the other thing that we can do is thinking about divergence. So we take the cleavage and we rotate it to bedding, and we see divergence to the left, okay, or counterclockwise divergence. So if we want to go to the next antiform, we'll find the antiform over there. That's the direction we need to work. And we know that this antiform is going to be an anticline as well, because the younging is right way up. Okay, we know that we are at the right way up of the right way up limb, because the cleavage is steeper than the bedding. Okay, so again, we get a lot of information. Okay, bedding is, well, that's the first thing that we recognize, that bedding is not perpendicular to cleavage, therefore we have to be at the limb. Yeah, that's a question that I ask every year in the exam. Yeah, you have a little outcrop, you see that the relationships are either perpendicular or non-perpendicular, and I ask you, are you at the limb of a fold or a hinge of a fold? So if the relationships are not, or if you have oblique relationships, you know that you're at a limb. You can work out divergence, that's the next question in the exam. And you know that you are structurally right way up because the cleavage is steeper than bedding. And you know that you are stratigraphically right way up because the younging is to the top. Let's look at these two examples that could be kind of part of the same structure. So here is what the bedding does here. Yeah, horizontal bedding and the cleavage dipping to the right. Yeah, maybe 45 degrees to the right. And then you go to the other outcrop and you see that the cleavage is doing the same. Yeah, and that's the important thing. I mean, if you see that the cleavage is going all over the place, then you must be dealing with more than one generation of folding. So the whole thing would work only if the cleavage, if we have one generation fold and the cleavage is consistent everywhere because it represents the axial plane orientation of that fold. So that's good. We went to the next outcrop and we still find that the cleavage does pretty much the same. And the bedding now is steep. Okay, so I think it's marked here. That's the bedding. Yeah, a little bit less clear perhaps. Yeah, as I mentioned before, sometimes when the rock is cleaved, the bedding becomes the trickier part to actually define. In the other photograph, it is of course clear. Okay, and we can do divergence here. So we take the cleavage, we rotate to bedding. That will give us a divergence to the right. And here we do the same bedding, cleavage. We take the cleavage, we rotate it, and it will give us versions to the left. So we know that there is an antiform in between the two outcrops. We know that is this one right way structurally? Is it right way up or overturned? Right way up. The cleavage is steeper than the bedding, and this one, the cleavage is shallower than the bedding, so that would be the overturned limb. Okay, and then we take our notebook and we start thinking what is going on here. So maybe, the cleavage is always the same, so there must be a fold here that has a cleavage that is moderately inclined. Yeah, these are moderately inclined type of folds. Yeah, we can work out also what the intersectionation is and know, so for example, horizontal intersectionation. So go to the classification diagram saying what kind of fold is that. But the important thing is that we think we were in one outcrop here, and that is the right way up outcrop, and we were on the overturned limb here on the other outcrop. Yeah, we didn't define the stratigraphy here. Okay, we need to look carefully and find if we have Youngin criteria. So we still don't know if this is an antiform, if this is an anticline or a syncline. What do you think is going on here? So would you be able to define a divergence here? Okay, so you can't do the divergence because the bedding is perpendicular to cleavage. You are basically looking at the hinge of a fold. And let's think what kind of fold is that. So the axial plane is vertical. The fold hinge is the intersection of bedding and cleavage. So by the look of it, it's shallow or gently plunging. Again, away from the photographer. So looking down plunge. So what kind of fold? How do we call this fold? A fold with a vertical axial plane. Upright, horizontal. Yeah, so upright stands for the axial plane, and we add a horizontal to indicate, or gently plunging. Of course, it's hard to see in the photograph whether it is gently plunging or horizontal. It doesn't look to be steep. Okay, so again, we have these diagrams with us in the notebook at the end of the notebook, so we immediately know how to relate that. And we think where we are in terms of the bigger scale structure, we have to be somewhere here. Yeah, we'll not be surprised if, these, as you can see here, these rocks are pretty competent. The cleavage is not very well developed. It's almost like a fracture cleavage. We expect to see if there are weaker units there, rocks that are more, that could deform more easily. Maybe they will create folds as well, and these folds will be M-style folds, so folds that do not have any vergence. Okay, so how are we doing with time? I think I will stop here because this basically is going to be a long discussion on this little outcrop. Okay, so we come to an outcrop here, we take a photograph, we take our compass, and we can spend good 20 minutes discussing what it means, and you will see that there's a huge amount of information that we can get from a single outcrop. And again, that's exactly what you will get in the exam. You will get a sketch like that, yeah, so kind of a sketch of an outcrop, and you will be directed to answer, all the, where is the next antiform, where is the next anticline, where is this an overturned limb or right way up, and all the kind of questions like that. So very important that you will follow exactly the logic of how we do that, but we will start doing that on Thursday morning. Bye-bye.
how are you? Good to be back. Oh, hello.
She's going to be with us off the hand.
As long as the weather's okay.
Here it's not, I think it was. If the weather's
If the
fine.
weather-
People who are experiencing for the first time are probably still like excited to get them. As long as we can keep going on.
Well, the wind's howling, it's raining.
Yeah.
My colleagues just up there. Checking out perfect sound.
We just got back from Noosa.
From where?
Noosa.
Oh, right.
Yeah, and it was nice. We didn't actually see a lot. We did hiking. We did the hiking. Yeah.
While I was in the car park,
She did tours too.
she did do some ceremony.
Yeah. A lot.
It's the car park.